So yeah, so coming to the equal variance part, it is the homoscedasticity that we were referring to, and it is the constant variance across the errors. And then doing the residual analysis, residual is nothing but the error that we are referring to, right? If y hat is the predicted output and y is the ground truth that we already have, and if you take a difference of that, that will become your basic error, right, that we were referring to. So yeah, so the residual of observation is the difference between its observed and predicted value, and you have to check some assumptions of regression by examining the residuals. So we have to examine the residuals. So the assumptions that we were referring to, as we saw them in the previous slide, right? So it is that in the sense, like, we have to use with respect to the residuals, we have to examine for the linearity assumptions. First one is linearity, right? LINE, right? L is linearity, I is independence, so we have to evaluate the independence assumption, and N is normal distribution, and E is nothing but the final set of thing, right? Whatever the equal variance is there. So we have to examine for the equal variance or the constant variance, which is homoscedasticity that we were referring to. And we have to do the graphical analysis of the residuals, in the sense, like, we have to plot the residuals versus the x value. So, for performing the residual analysis and trying to understand or interpret the relationship, whatever the relationships are there, or whatever the assumptions are there with respect to the regression, we are trying to do them with respect to the residuals itself. So, suppose if you see it here, you can see the relationship between x and y here. So yeah, so we will see, like, is it a linear relationship or not? It's a secondary thing, but now if you see the x and y values, you can see that clearly there is no linear relationship that is existing between x and y, right? So if you see even the residuals, by seeing the residuals, they are not linear, right? Residuals. So from that you can conclude that even the relationship between x and y is also not linear. And if you see the case here, this set of residuals, you can see that if the residuals look like this, then you can assume, or you can interpret that they have a linear relationship between x and y. And regarding the independence condition, so to understand the independence, so if you see the residuals, and if you try to plot the residuals with respect to x, you can see that there's a sort of like set of like variations that you can observe, right? If you see this sorry, it's a linear variation that you are observing here, and if you see, you have a curved variation, so you have some sine wave kind of curves that are that you can see, right, with respect to the residual and x value. But if you see it here, there is no such form, or that is there is no such kind of relationship between the residual and x. That is the reason you can conclude that they are independent. So by seeing or analyzing the residuals and plotting them with respect to x, you are going to interpret what are the different set of things regarding the relationship between the x and y. And now a normal probability plot of the residuals can be used to check for normality. So once you have plotted this, so you have plotted the residual with respect to the percentage, right? We can see that residual analysis for equal variance. So if you see, if you get if you see the residuals, if the residuals look like this, then it signifies that there's a constant variance that is there between the residuals. So you can also check the residuals as well. But if you see these kind of relationships, if you don't have any these kind of plain sort of relationship, if you see these kind of relationships, then it signifies that you don't you have a non-constant variance. So even if you check it here, non-constant variance is nothing but if you see the residuals here, you can understand, right, they are non-constant. And even the relationship between x and y also, with respect to the variances, if you see, that is also not constant, which you can easily understand by looking at the two different pictures that are shown here, right? And now we have to measure the autocorrelation. There is something called this Durbin-Watson statistic. So it is used when data are collected over time to detect if autocorrelation is present. So with respect to time, we are trying to collect the data, and we are trying to check is there any autocorrelation that exists. Yeah, autocorrelation exists if residuals in one time period are related to residuals in another time period. So if you see, if you want to check for the auto correlation part, auto correlation is correlation of the errors over time. Whatever the residuals are there, if there is any correlation between those errors with respect to time. If you see the cylindrical pattern kind of pattern here, so you have a residual plot here with respect to time. You are plotting the residual, and you can see that you have a cyclic relationship, right? So you can see the repetition of it. This has occurred, and you can see again there's a repetition that is occurring. So here residual show us cyclic pattern, not random. Cyclic patterns are a sign of positive autocorrelation. So if you have this kind of cyclic pattern that you are observing, then it signifies the positive autocorrelation, and it violates the regression assumption that residuals are random and independent. And the Durbin-Watson statistic, if you consider, it is used for testing the autocorrelation part. And we have the H naught and H1. So H naught is nothing but the null hypothesis, and H1 is the alternative hypothesis that we are going to propose when we are rejecting the null hypothesis, or we are not accepting that, we are going to the alternative hypothesis, right? As we have already discussed in the basic stats part, stats related module in the internship. And H naught is nothing but residuals are not correlated. So this is what your null hypothesis is, and the alternative hypothesis is positive autocorrelation is present. So now we are going to do the statistical test. So we already saw a different set of tests, like T test we saw, and other F test, and other set of tests also we saw, right? We saw chi-square test. So different tests we already saw, and we have an idea of how we are going to do this sort of statistical test. So to do this kind of test, the possible range is 0 less than or equal to d less than or equal to 4. So the possible range is of the d is between 0 to 4, and d should be close to 2 if h naught is true. So null hypothesis to be true, it should be closer to d 2, and if it is less than 2, it signifies that there's a positive autocorrelation that is existing, and if it is greater than 2, then it will signify a negative autocorrelation. So this is how we are going to interpret the things. And if you see the d value, this is how we are going to calculate the d value, and 0 to 4 is a possible range of that. And coming to the testing for positive autocorrelation, once you calculate the statistic, then you can see that you have something called the DL and DU bounds or thresholds that are present, and you can find this DL and DU from the Durbin-Watson table that is present. And for that particular sample size and the number of independent variables k, you are going to get those DL and DU values, and you are going to calculate your Durbin-Watson test statistic, which is your D, as we saw previously, using any Excel or Python or any kind of statistical package or any general library that is available. And once you calculate that, then you are going to check it, whatever the d value you got, you are going to check it with respect to the DL. If it is less than that, you are going to reject your null hypothesis, and you have to go to the alternative hypothesis. And if it is between the DL and DU, it is inconclusive. You cannot conclude anything properly with a good amount of confidence. And if it is greater than DU, you are not going to reject your null hypothesis, and you are going to accept your null hypothesis. So the range is between 0 to 2, and according to this, you are going to take a respective decision. And yeah, this is how you are going to test for the positive auto correlation. And suppose we have the following time series data. Suppose this is the time series data you have, and with respect to time, you have the sales data, and you have already fitted a model across it. And you have this is the model that you have fitted, and this is the R square value that you have updated. Is there auto correlation? So the question is to identify or to understand the auto correlation part. So you have n equal to 25, so you have 25 samples, and you have calculated the sum of square difference of residuals and sum of spared residuals, and from that you are going to obtain your d value. And if you see the d value, you got or obtain this d value, and if you try to fit it across, you can see that whatever the dl, yeah, so with respect to the Durbin-Watson table, you can see that for the respective n value and k, you can see that this is the dl and du that you are going to obtain. and you can see the d value as well. So this is what the d value is, and you are going to reject your null hypothesis. Why? Because whatever the d value that is obtained, it is less than the TL, right? So that is what the condition we are supposed to, or that we are to see. Previously we have discussed the same, right? And then regarding the inferences about the slope, yeah, the standard error or the regression slope coefficients, whatever the b1 is there, b1 is nothing but the slope that we were referring to, right? So you can see that the SB1, whatever the standard error with respect to the regression slope coefficient SB1, you can see how you are going to calculate that. You have the SYX divided by root of SSX. If you do, you are going to get that, and SB1 is nothing but the estimate of the standard error of the least square slope. So this is how you are going to get that, and SYX is nothing but the standard error of the estimate that you are going to calculate. And comparing the standard errors of the slopes, if you see, SB1 is a measure of the variation in the slope of regression lines from different possible samples. So if it is small, SB1 is small, you can see the different set of models and the possible variations, and if it is large, you can again see the set of possible samples here. And what are the pitfalls of regression analysis? So lacking an awareness of the assumptions underlying least square regression. So yeah, so we have to somehow from the residuals itself, we have to understand the underlying assumptions. Are the assumptions true or not? Whatever the line acronym that I have explained you, right? With respect to that acronym, we have to do all the residual analysis, and we have to finally conclude that the set of assumptions hold or not. If they hold, then whatever the least square regression or the linear regression model that you are trying to fit, it makes a proper fit for the data. Else we have to think further regarding the modeling part. And not knowing how to evaluate the assumptions, obviously you cannot directly evaluate the assumptions, right? That is the reason we are going for the these kind of residual analysis that we were referring to. And not knowing the alternatives to least square regression if a particular assumption is violated. Yeah, once it is violated, then alternative you have to take, right? You cannot apply this direct least square regression. And using a regression model without knowledge of the subject matter and extrapolating outside the relevant range. So yeah, these are the different set of things. And what are the different strategies for avoiding the pitfalls of regression? So you are starting with the scatter diagram of x versus y to identify the possible relationship, and then we are performing the residual analysis to check the assumptions, and we are plotting the residuals versus x to check the violations of assumptions, such as homoscedasticity, in the sense the equal variance that we were referring to, right? Equal or constant variance in the regression. And we are going to use a histogram and a box and whisker plot and normal probability plots or plot. So we are doing all these different plots of the residuals to uncover the possible non-normality. So the assumption, one more assumption is normality one, right? So we are trying to check that also. And is there if there is violation of any assumption, use alternative methods of models. If there is no evidence of assumption violation, then test for the significance of the regression coefficients and construct confidence intervals and prediction levels. Avoid making predictions or forecasts outside the relevant range. And coming to the multiple linear regression part, our model is y equal to beta naught plus beta 1 x1 plus beta 2 x2 and so on. If you see the difference between the general regression and the multiple linear regression, you can see the coefficients, right? So you can see the if you see the general linear regression, it is only this much, so up to x1. But if you have more number of features or the independent variables, they are x1 x2 and up to so on up to xp, right? So we are going to take them into consideration, and we are going to take the respective set of things. And if you take the example of the sales data that we are referring to previously, this is how we are going to model the sales data with respect to the three different variables that are present or the features that are present, and how we are going to interpret the regression coefficients. Uh, yeah, claims of causality should be avoided for observational data. So we are trying to see only correlations. We are not very much particularly regarding the causality, but we are more particular among the correlations that are present. That is the reason we are plotting the scatter plot and try to identify the relationships, right? Yeah, a regression coefficient beta j estimates the expected change in y per unit change in x with all other predictors held fixed, but predictors usually change together. So as I have told you, there's a relationship between the predictors as well, right? How we are going to deal with it in the sense I'll explain you in the upcoming things. And essentially, all models are wrong, but some are useful. And the only way to find out what will happen when a complex system is disturbed is to disturb the system, not merely to observe it passively. So we have to be more active, and we should be understanding how we are going to interpret the data, or what are the relationships that are between the features and between the independent and dependent variables, and how we are going to fit the best model that is possible for that particular data with the knowledge that we have and the restrictions we have. Why? Because suppose if the relationship between x and y is not linear, then we have to fit the linear regression, right? So that will become a problem for us. So based on the limitations that we have with respect to that, we are going to make our own assumptions, and then we are going to make a best possible fit of the model. And we have this set of estimates, and with respect to that, you are going to predict your y cap, and you are going to calculate the RSS. And if you see, it's something similar. Whatever the RSS that we are calculating, or whatever the y cap, everything is similar to the general linear regression. But here we have more than x1, we have x2, x3, and so on up to xp. Here also the same case. And you can see, if it is a plane, we were seeing the same thing in the line case, right? Whatever the residuals that you are going to calculate or that we are going to get. And now if you are seeing it in the as a plane, you can see it for visualization. And we got the results regarding the t statistic and the p value for the TV, radio, and newspaper. And yeah, so we have this different sort of questions in your mind. Is at least one of the predictors useful in predicting the response? Do all the predictors help to explain why, or is only a subset of predictors useful? How well does the model fit the data? Given a set of predictor values, what response value should we predict, and how accurate is our prediction? So just try to understand these questions, and try to find the answers yourself. How you are going to understand this? Why? Because with respect to the discussion that we are making comprehensively in the regression part, you should be able to understand and interpret and answer those particular set of questions. Yeah, for the first question, we are using the F statistic. And yeah, so deciding on the important variables, we can compute the least square fit for all possible subsets, and then choose between them based on some criteria that balances training error with model size. So we have to try to understand that. And however, we often can't examine all the possible models that are there, right? It will be like 2 power p, which will be like over a billion models. So we are going to use some automated approach and try to take a particular subset which narrow down to a search space. And we are going to start with the null model, and we are going to start with respect to the RSS that we have calculated. We are going to use some stopping rule, and we are going to iterate, and we are going to find the respective p values, and finally try to see the set of values which are important for us. And in the same way, in backward selection also, in forward selections, you are going to assume a null model, and you are going to add the set of variables one by one. Variables you are adding x1, you are adding x2, you are adding, so you are adding. In backward selection, you are going to remove each and every variable and try to check for the residuals, and try to check the p value as well, and try to see the how the significance level is changing. And with respect to that, you can understand the significance of a particular variable or the weight of a variable for the predictions that you are trying to make. And then yeah, so to choose the optimal member in the path of models produced by forward or backward stepwise selection, we have something called this EAC and BAC criteria, and along with that we have something called this adjusted R square. Also, in the sense, like if you see the general R square, whatever the R square that we have calculated, as we keep on increasing the number of features, it keeps on improving. So because of that, you cannot directly conclude or get a direct idea regarding the variation in the model. So that's the reason we are going for a adjusted R square here. And yeah, so we have other considerations in the regression model as well. Some predictors are not quantitative but are qualitative. They are taking a discrete set of values. They are called categorical predictors or factor variables. So if you try to see a scatter plot and try to understand that, you are going to get that. And removing the additive assumption. So we have these interactions and non-linearity, right? Interaction is nothing but if you see these three different set of variables or features as we were discussing previously. You have TV, radio, and newspaper, right? So there is always a relationship between TV and radio and newspaper. So if you have this kind of relationship, that relationship is called interaction. So there's an interaction that is present. In marketing, this is known as synergy effect, and in statistics, it is referred to as interaction effect. And interaction in the advertising data. Then the levels of either TV or radio are low, then the true sales are lower than predicted by the linear model. But when advertising is split between the two media, then the model tends to underestimate sales. So yeah, so now what you are going to take is, you are going to take the interactions as well. So along with the TV and radio part, you are going to take the radio into TV, a product of radio and TV. So we have considered the interaction part also in our model building. And yeah, so you have this interaction as well, and you have to make sure that we can calculate the p-value and try to understand the significance of a particular term. And even the TV radio part is extremely low, right? It signifies that the relationship between TV and radio, or the interaction, is not that much significant, or that is not contributing much to the model. But you cannot directly yeah, so that is one thing. And one more thing to keep in mind is, suppose you are keeping the interaction term, then you have to keep the TV and radio as well. So you have the TV, radio, and TV here. So for sure you have to keep the TV and radio as well. Why? Because you cannot even if it is not contributing, you cannot remove a particular variable. If you cannot remove TV, why? Because we have the interaction that is all present in the model. You have to keep the other two variables as well. So this is regarding the interactions that we were referring to. Yeah, and then we are trying to calculate the set of values with respect to the radio and with respect to the TV. Yeah, and sometimes it is in the case that an interaction term has very small p-value, but the associated main effects do not. If we include an interaction in a model, we should also include the main effects, even if the p-values associated with their coefficients are not significant, whichever I have already explained you the scene, right? The rationale for this principle is that interactions are hard to interpret in a model without main effects. Their meaning is changed, particularly S, right? Why? Because when you are keeping the interactions, you have to keep the individual ones also, like TV and radio. Also, you should keep when you are keeping the product of TV and radio. And the interaction between qualitative and quantitative variables as well. If you see, you have two different set of values, right? You have the qualitative variables, and you have the quantitative variables. So there's an interaction that is there between them also, and even that is the case, then you have to model it accordingly. And if you see here, there is no interaction between income and student, and if you see it here, there's an interaction term between income and student that is present. So, and then the nonlinear effects of predictors. So if you see, whatever the auto data that we are referring to, right, MPG data, which we have already plotted and saw in the code. So you can see that you have the polynomial regression also, right? So this is the linear regression time, and linear regression type, and this is the polynomial sort of regression that we were discussing about. Or you can see, and we have already also tried to calculate the respective scores, right? And you can see that polynomial regression is doing much better than the general regression term. And yeah, so you can see the NPG value here, and you can see the polynomial term here. So you have degree 2, right? Polynomial horsepower. And if you see, we have the generalizations of the linear model. So yeah, so we have the classification problems. We have yeah, so this is a basic model that we are going to discuss for the regression. And moving further, there are different types of problems that we are going to discuss. You have something called these classification problems, in which like there are different sort of algorithms like logistic regression and support vector machines that we are going to discuss. And we have this ensemble based models, we have tree based methods like decision trees, and we have the bagging algorithms, and we have the random forest and boosting related algorithms. And we have something called the regularized fitting, ridge regression, and lasso. This is nothing but the general regression itself, but you are going to add the regularization part to that. And you have the non-linearity in the sense like, if you see the SVMs, right, those kind of models where you have the kernel smoothing, and we have other set of models, and we have the nearest neighbor methods in the non-linearity case. So we have all these different generalizations and different set of models that are coming up.